This is ABC Fora.
Yeah, so I'm going to talk actually not so much about my own work, that'll come up a little bit, but just about the theory of prime numbers in general, the number theory, which is one of my favorite areas of mathematics. It's of course not the only area of mathematics, but it's one of the major ones. Kurt Mahler, for instance, did a lot of work in number theory, so I'm quite honored to be giving lectures in his name. It's a very old topic, it's a very huge topic. There's no way in a public lecture like this I can tell you everything that's going on. I don't even know everything that's going on. So I'm going to just give this very, very quick tour. The way I like to describe it, it's like visiting Paris and only seeing the Eiffel Tower and the Arc de Triomphe. You know, it's not really the full story, but it's something. Okay, so but it's about the prime numbers, and just to remind you, everyone, what a prime number is. A prime number is any natural number bigger than 1, which can't be factored into two smaller numbers. And so up there, we have the first few prime numbers, and they just go on and on and on and on. The biggest one that we know of is down there. Okay, so we found a lot of primes. They've been studied for a long, long time. In fact, the ancient Greeks were the first people to study them systematically. In fact, even Euclid in his Elements had several results on the prime numbers. And they proved the first two really important theorems about the primes. And that's a starting point for everything else. So the first thing we know about the primes is what's called the fundamental theorem of arithmetic. And it says that every natural number bigger than 1 might not be prime, but even if it's not prime, you can always factor it into primes. Every number is either prime or the product of primes, and there's only one way to write every number as a product of primes, other than rearranging. So 10 is 2 times 5, or 5 times 2, but that's the only way to split 10 into primes. That's the fundamental theorem of arithmetic. The other major theorem that they proved is called Euclid's theorem. So Euclid proved many theorems, but this is the Euclid's theorem, that the primes go on forever. There are infinitely many prime numbers. The primes never stop. Okay, so these are the two basic theorems in Greek prime number theory. So the fundamental theorem that every number can be split up into primes, one way to think about it is what it tells you is that the prime numbers are very important to integer multiplication. They're like the atoms. If integers are like molecules, then prime numbers are like atoms. They're the atomic elements of integer multiplication. Every molecule is made up of atoms, carbon dioxide, CO2, and similarly, every integer is made up of primes in exactly one way. And so here are a couple of numbers, and they're prime factorizations. By the way, this is, by the way, the main reason why we don't consider 1 a prime number. So, of course, 1 has no factors other than itself. So you're saying, why don't we call 1 prime? Well, if we called 1 prime, then there'd be more than one way to split up a number into primes. Like the number 10 could be 2 times 5, but also 2 times 5 times 1, 2 times 5 times 1 times 1. And you wouldn't have a good, unique prime decomposition. And so you wouldn't have the fundamental theorem of arithmetic. And we really like the fundamental theorem of arithmetic. So we have demoted 1, and we do not consider it a prime anymore. Okay. So Euclid's theorem is a theorem that there are infinitely many primes. And I want to show you the proof of it because it's a beautiful proof. It's one of the first proofs, in mathematics, but it's still a classic. It's a real gem. It's what's called a proof. It's a reductio ad absurdum proof, a proof by contradiction. You prove something is true by proving that it's not false. It's an indirect argument. So I'll just show you how it works. So you want to prove that there are infinitely many primes. So you suppose there weren't. Okay, suppose that Euclid was wrong. Suppose there are only finitely many primes in the world, that after a while they just stop. So for the sake of argument, suppose that 2, 3, and 5 were prime, but then there are no further primes. Suppose that you can only find finitely many primes. Then what you can do is that you can take all those primes and multiply them together. So if 2, 3, and 5 are all the primes in the world, you multiply 2 times 3 times 5, you get 30. And then you add 1. You take the product of all these primes, you add 1 more, gives you a new number, in this case 31. Okay, so you take all the primes in the world, multiply them together, add 1, that gives you a new number. Now why do you do this? You do this because this new number is 31, is bigger than 1, clearly, and because it's 1 more than a multiple of all the primes in the world, it's not divisible by any prime. Okay, it's not divisible by 2, 3, or 5. It leaves a remainder of 1. Okay, so we have found a number which is bigger than 1, but it's not, it can't be divided into primes. But the fundamental theorem of arithmetic tells you that every number can be divided into primes. And so because we know the fundamental theorem of arithmetic, we have reached a contradiction. So there can't be finitely many primes, and hence there must be infinitely many primes. That is Euclid's proof. So that's an amazing proof. I mean, it's sort of, you know, it takes a while to get used to these sort of indirect type of arguments. There's a famous quote by the British mathematician G.H. Hardy about this. He said that reductio ad absurdum, which Euclid loves so much, is one of a mathematician's finest weapons. It is a far finer gambit than any chess gambit. So in chess, you may sacrifice a pawn or a piece to gain some advantage, but a mathematician offers the entire game and still wins. So, okay, so it's a great technique. Okay, so these are the two basic theorems. Okay, so that's great, but actually there's a lot more to these theorems than just the fact that they're true. So for example, the fundamental theorem of arithmetic tells you that every number can be factored into primes in principle. So given any number, you know, 1,337, given enough time, you could figure out how to factor it into primes. But no one knows how to factor large numbers very quickly. You had to take a really big number, let's say 100, 200 digits long. Eventually, you know, you could factor into primes, but it would take you an extremely long time. If it's 100 digits long, it may take you longer than the age of the universe before you finally factored it. And this is actually very important because there are many algorithms, there are many cryptographic protocols, codes that are used daily, you know, in, such as the RSA algorithm, which I think is used in ATM machines actually, the reason why they can't be broken is because no one knows, because they use very, very long numbers which no one knows how to factor into primes. If they did know how to factor these large numbers into primes, you could break these algorithms, but no one knows how to do that, and so we believe these algorithms are secure, at least for the moment. So, in fact, the fact that we don't actually know how to execute this fundamental theorem in practice is actually very important. It's a similar story with Euclid's theorem. We know that there are infinitely many primes, but so in principle, you know, if you wanted 1 trillion primes, eventually you should be able to find 1 trillion primes. But no one knows how to actually just deliver all these prime numbers other than just very laboriously counting them. There's no recipe to find, say, the millionth prime, the billionth prime, the trillionth prime, other than basically by counting one by one. It's not like other sequences, like the square numbers. Okay, the millionth square number, I can tell you what that is. It's a million squared. Okay, but the millionth prime number, I can't tell you so quickly. Okay, so in fact, it's quite hard to find really big prime numbers. The largest prime number that we actually know is this guy, 243,112,609 minus 1. It's a huge number, almost 13 million digits long. There's an Australian radio host, actually, Adam Spencer. You may know him. He has a breakfast show. And he once gave a talk, and he had some mathematics in it, actually. And he showed this prime. He actually had some students come up. He had printed this prime on this printer paper, this old-style printer paper, which was all perforated. And they had the students unwrap the entire the digits of this prime. They went all around the room. It's a huge number. It was shown to be prime by actually a big internet search. It's called GIMPS, Great Internet Mersenne Prime Survey. It was a project that distributed the task among thousands and thousands of computers across the internet. Okay, so primes are hard to get a hold of. As I said, it's hard to find, say, the millionth prime number, and because the primes are doing something funny. I mean, they're kind of irregular. As I said, there's no good formula for the nth prime number, and they tend to behave very randomly, and we don't really know what patterns exist inside them, what patterns don't exist inside them, because they look so much like random noise. And it's because of this that the primes have been much more difficult to study than one might think at first. There's a lot of very simple questions about the prime numbers that even after thousands of years of work, we still don't fully know how to answer. So one of the simplest ones actually is what's called the twin prime conjecture. So we know there are infinitely many primes, but we don't know whether there are infinitely many twin primes. So a twin prime is a concept invented by the ancient Greeks, is a pair of primes which differ only by 2. So p plus 2, like 3 and 5 are twin primes, 11 and 13 are twin primes. There are not as many twin primes as primes, but there's still a lot of twin primes. Here are the first few twin primes. And we think they also go on forever, but we don't know. The largest pair of twin primes ever found is this pair down here. This was found by a computer search a few years back, but for all we know, that's actually the last one. There may be no more. We think they go on forever, but we don't know actually how to prove that. Okay, so there's a lot of things that are very simple about the primes, very basic questions that we still can't answer, and it's because they behave so randomly. There's a quote by the Hungarian mathematician Paul Erdős about this. So Einstein made a famous quote that God does not play dice for the universe. He was talking about quantum mechanics. So Paul Erdős said, well, yeah, okay, God may not play dice for the universe, but something strange is going on with the prime numbers. The prime numbers are not random. I mean, there's only one set of prime numbers in the world. You don't have to roll any dice or flip any coins to create the prime numbers. But nevertheless, they do behave a lot. The prime numbers behave as if they were just some random sequence of numbers in many ways. Okay. So we do believe the primes behave randomly in a number of ways. And this is actually a very important belief for us because it underpins our confidence in a lot of cryptographic algorithms, in particular something called public key cryptography, which is another cryptographic algorithm which is used everywhere. If you're buying something over the internet using your credit card, and you're using a secure connection, your credit card is being encrypted by a public key algorithm. Okay, lots of things on the internet these days are encrypted. Of course, people can hack in and so forth, but when the security of the internet has been compromised, it's never because of the codes. It's because of something else, sloppy programming or some human error or something. But the mathematics is secure. Cryptography is this complicated subject. I mean, just because you have a good code doesn't guarantee everything else is secure. Like you had a nice lock on your door if the window is open, it doesn't help. But anyway, we do at least know that these locks are pretty strong. Okay, so let me explain what public key cryptography is, because it's a beautiful concept and one which initially you might think shouldn't work at all. So I'll give you an analogy first, a physical analogy to what public key cryptography is. Suppose you have two friends, and in cryptography, the two friends are always called Alice and Bob. I don't know why. That's just the way they are. That's the way it is. So you have two friends, Alice and Bob. And Alice has a box of something very valuable, and I'm going to call it G for reasons that, it may become clearer later. So she has a box called G, and she wants to send it to her friend Bob. But her friend Bob is really far away. Maybe she lives in Australia, Bob lives in America or something. So she has to mail it. Okay? But she doesn't completely trust Australia Post, and she's worried that someone handling this box is going to open it and take out what's inside. Okay? So she wants to protect the box. Now, of course, what you can do is that you can lock the box. Okay? So she could put, say, a padlock on the box, and then now people can't open the box. Let's assume the box is unbreakable, just for simplicity. So now you can send a locked box over to Bob, but that doesn't help Bob because Bob would then receive a locked box, and he doesn't have the key for that box. Okay, so you could also try setting the key, but Australia Post, if they can pick up the box, they can also pick up the key. And so how would you? How would you be able to send something securely with Bob in such a way that no one who's intercepting can take out what's inside? So this is basically the public key cryptography problem. So it's not immediately obvious you can even do this, but you can. There are many ways to do it, in fact. So I'll give you one solution. So one solution is called a three-pass protocol. So suppose Alice wants to send the box G to Bob. So she does what I said before. We'll lock the box. We put a lock on it. I'll call it lock A. And now we have a locked box, which I call G to the A. So we have this locked box, and we send it to Bob. So Bob now receives a locked box. Alice keeps the key. Okay, Alice is the only one with the key A. Okay, well that doesn't do Bob any good. He has a locked box. So what he does is that he takes that locked box and locks it again. Okay, so he picks up his own padlock, puts another lock on the same box, calls it B, and now we have a doubly locked box, G to the AB, with Alice's lock and Bob's lock on the box. And she sends the doubly locked box back to Alice. Now, why would you do that? Well, so Alice, of course, can't do anything about Bob's lock, all right? Because Bob keeps the key. But she can do something about her own lock. She can now take her own lock off. Okay? So now she takes off her own lock from the box. Now there's only Bob's lock left. And now she sends the box back. Okay? And now Bob gets the box with his lock on it. And then he can unlock it and get back the box. Okay? So this is a 3-pass protocol. You have to send it back and forth 3 times. But it works, and it is secure. Okay? If you have someone in the middle, and in cryptography, the eavesdropper is always called Eve. If you have an eavesdropper, Eve, all she ever sees is 3 locked boxes. She never sees the unlocked box. Okay? So this is the 3-pass protocol. I've heard that this is actually used by some military people to transfer sensitive documents. At least that's what I've heard. I have no proof. But anyway, this is the physical protocol. But you can do the same thing with numbers. Okay? Suppose you want to send, instead of a box, you want to send a number. You know, a credit card number, Swiss bank account number. There are many numbers that you don't want you want to send securely. Okay, so you have a number G, and you want to send it. Alice wants to send it to Bob, say by email, and she doesn't want anyone watching the email to get the code. You can do it too. And there's exactly the same protocol works, and it's called the Massey-O'Meara crypto system. So the way it works is that, okay, so first of all, they talk beforehand, and they have to agree on a very large prime number. Now, maybe they pick one of the prime numbers I showed you before. So you pick a very large prime number. It doesn't really matter what number it is, as long as it's large and prime. Okay, now that's public, so even the eavesdropper will know that there's a prime number P. But this won't help the eavesdropper. So you pick a large number P. Now, Alice has her secret number G. So she locks it, and the way you lock it is that you raise it to the power A. So you raise G, you raise it to the exponent A. And then you divide it by P and take the remainder. So that kind of mixes up G to the A quite a bit. If you don't, and then she just sends that remainder, G to the A modulo P, the remainder modulo P, that scrambled number to Bob. It's important you take modulo P, because if you just take G to the A, you can start taking roots and logarithms and recover G. So you have to scramble it by doing this modulus. So she sends G to the A to Bob, sorry. Okay, so Bob then can't unscramble G because Bob doesn't know what A is. So then Bob locks the number again by taking G to the A and raises it to another power. He picks his own secret number B, raises it to B. Now you have G to the AB mod P. And so that's another scrambled number, sends that back to Alice. Alice can't do anything about the B, but Alice can take an 8th root. There's a way to take an 8th root of a remainder mod P, which I won't talk about. But Alice can take the 8th root of G to the AB, gets back G to the B, sends it back to Bob, and now Bob can take the Bth root of G to the B and gets back G. Okay? So it's exactly the same algorithm as the physical algorithm, just implemented numerically. And people actually use this. There are actual cryptographic protocols out there used daily, which use basically this type of algorithm. Yeah, so I mean, this is a very practical algorithm. Now, we believe it's secure. Oh, yeah, okay, yeah. So I said that already. You need the prime, otherwise you can use logarithms to crack the code. Yeah, so we believe, but we can't prove yet, we believe that these algorithms are secure, that if you take really big numbers, G and P and so forth, and you use this algorithm, then an eavesdropper can't crack the code in any reasonable amount of time. It turns out that if an eavesdropper has like an infinite amount of time, eventually she can crack the code by trying all the G's and A's and B's and eventually finding a match. But that's called brute force. But brute force would take trillions of years. We believe there's no practical way to crack these codes, but we have no proof of this. There is a very important problem in mathematics called the P equals NP problem, which is, again, I could give a whole talk about P equals NP. But P equals NP, roughly speaking, or P not equals to NP, actually, roughly speaking is the statement that there exist problems that are genuinely hard. They're easy to state, but hard to prove, hard to solve. And cryptography should be an example of this, right? Codes that are easy to generate but hard to crack. But we don't know how to prove this. The Clay Mass Institute, which is one of our sponsors here, actually, made seven different prizes for 7 major problems in mathematics, each with $1 million prize attached to it. And the P equals NP problem is one of them. So, okay, but no one has solved that. Only one of the 7 has been solved so far. Okay, but we do have some partial progress. So just to give you a taste of the type of thing that we can do, as a result of my friend, Jean Bourgain. So he showed that in this protocol, the eavesdropper never sees G. The eavesdropper just sees these 3 scrambled numbers, G to the A, G to the B, G to the AB. And so what my friend Bourgain showed is that these numbers that the eavesdropper sees, they're what's called uniformly distributed. What that means is that if you just look at the most significant digits, forget about the lower digits, but just the biggest digits look just like random bits, random noise, random digits. And so that's all the eavesdropper sees. And so what that tells you is that if the eavesdropper only sees the most significant digits of these numbers, she can't do anything with them because they just look like random noise. And the only thing you can do with random noise is generate more random noise. You can't reconstruct anything. So that's evidence, that's partial evidence that the algorithm is secure, but it's not, there's nowhere near a complete evidence because, of course, there's these least significant digits as well, which are also important. So we don't know that. Okay. Okay. So, all right. So that was a demonstration of some sort of randomness connected to the primes. So the primes do behave randomly in many ways, but in many other ways they don't actually. So I told you before that I have no way to tell you, no quick way to tell you exactly what the millionth prime is, the billionth prime, the trillionth prime. The nth prime number, I have no quick, simple formula to tell you what that is. But, and it's because the primes fluctuate so randomly. But interestingly, the primes do there's a very important approximate formula for the nth prime, one that doesn't give you the nth prime exactly, but gives you something very close. So there's something called the prime number theorem proven over 100 years ago that says that the nth prime number is not exactly equal to anything we know of, but it is approximately equal to n times the natural log of n. So, the millionth prime is roughly 1 million times the natural log of 1 million, which I think is like 10 million or something. So that's a remarkably good approximation. In the background here, we have 3 lines, not so easy to see, but the dotted line, I think, is the graph of the nth prime. So this is n, and this is the nth prime. And the solid line is the graph of n log n. And they're pretty close. You know, if you look at the millionth prime number, and you look at million log 1 million, they're within like 2 decimal places of each other. This is the prime number theorem. There's actually a more precise formula for the nth prime, which is more complicated than n log n, which I won't write down here. There's a more precise formula which should be even more accurate than the prime number theorem. But we don't know that either. So so one of the other 7 Millennium Prize problems I mentioned is something called the Riemann hypothesis, which I won't state here. But what it says is, it's equivalent to the statement that there's a very precise formula for the nth prime, which is accurate to really high accuracy. If you take, say, the millionth prime number, you plug in this formula, you get accuracy to about 6 or so, maybe 4 or 5 significant digits. The formula that the Riemann hypothesis predicts is the dashed line. You can't really see it because it's lining up with the dotted line so well. It's an extremely good prediction. Okay, so that's another $1 million prize problem. I don't actually recommend you go home and try these. They're actually quite hard. But anyway. Okay, so I showed you, so you can think of the prime number theorem as a really souped up version of Euclid's theorem. Euclid's theorem tells you that the primes go on forever. The prime number theorem tells you sort of where they are. Not only they're infinite, but sort of where they are. And it's really an amazing theorem. It's one of the it's another landmark theorem in the subject. And I want to show you the proof. Well, not the whole details, but just sort of an idea of the proof. In part to show you just how much mathematics has advanced from say Euclid's day to say 1896, which is when this theorem was proven. It's advanced more since then, but I just want to show you this one theorem. So it's proven by a much more modern method than proof by contradiction. So it works like this. Okay, so what you do is that you want to understand the prime numbers, 2, 3, 5, and so forth. So the way you do this is that you actually create what I call a sound wave, or more precisely a function. And the function's name has a name. It's called the Monod-Rangold function. And this is a wave. It's a wave of sound, and it's a mathematical wave. And it's loud when time is a prime number, and it's quiet when time is not a prime number. So it's a sound wave that encodes the primes. So time 1 is quiet, time 2 is a noise, time 3 is a noise, 4, 5, 6, 7, 8, 9, 10, 11. So there's just some sound wave. Okay, so you create this function. And then what you do is that you listen to this function. Now, you listen to this function mathematically, And what that means is that you analyze this function by taking what's called a Fourier transform, which is one way of listening to a wave. Actually, technically, you take something closely related to a Fourier transform called a Mellon transform, but basically a Fourier transform. Much like the ear, actually, if the ear hears a sound wave, it will break it up into notes. The ear actually has some organs in it which do things like Fourier transforms. So you listen to this wave, and you hear all these notes. Okay, and there's actually a formula that in fact tells you what these notes are. These notes have a name. The notes you get here in this music are called the zeros of something called the Riemann-Zeta function, which I won't define here. So every zero of the Riemann-Zeta function is some pattern. It's an oscillation in the prime numbers. On the back here, the graphic here, what this picture is plotting is the reciprocal of the zeta function. So every time the zeta function hits 0, the reciprocal goes off infinity. So every spike here is one of the zeros of the zeta function, and they go on forever. So there's this music with all these notes. The problem is that if there's a really loud note in this music, then what will happen is that there'll be a big fluctuation in the formula for the nth prime number, and you would see that the prime number theorem would not work. There'll be a huge fluctuation. So there are these certain loud notes which would destroy everything, and so the whole game is to show that certain really bad notes don't appear. And this is a bit tricky, and I won't say how it's done. But once you have that, you then use some modern mathematics. You have to use either Fourier analysis or a tool from complex analysis called contour integration. But once you know that certain zeros don't appear, you have what's called a zero-free region, and you use some advanced analysis, then you can prove this prime number theorem. And if you knew more about these notes, then you could prove more than the prime number theorem. And in fact, the Riemann hypothesis is normally phrased as a statement about where all these notes are, these zeros. But I won't talk about that. Okay. So the prime numbers are really a funny thing. I mean, are they random? Are they not random? They're sort of a mix of both. That's sort of what makes them so fascinating. So on the one hand, we have the prime number theorem, which says that they have large-scale structure. So as you keep going on, they fluctuate a little bit, but they have a fairly uniform distribution. But if you look at small scales, they look quite random. So you can see this in this background picture here. So what these black dots are prime numbers. So what's going on is that we're just sort of ordering the numbers 1, 2, 3, 4, 5 just as pixels, just all the way down the screen. There's like 20,000 of these things. And every black dot is a prime. So I don't know if you can see it, but there are 2 black dots on the corner that are adjacent to each other. Those are 2 and 3. And then the next black dot next to that is 5 and 7, and there's a gap to get to 11, and so on and so forth. So you have all these black dots, and you can see that they're just sort of strewn around randomly. They get slightly sparser as you go down. There are fewer and fewer of. I mean, there's still quite a lot of them. I mean, they're going forever, but they get a little bit sparser as you go down. This comes from the prime number theorem. The gaps between n log n, the gaps between adjacent numbers in n log n, it grows a little bit. So slowly they get sparser and sparser. Here, there's quite a few. Down here, they're sparse. But otherwise, they look kind of random. There's those patterns. They sort of go around in various patterns, but they're not all that organized. Or unless you look at them a bit more closely, because there are some patterns here that you can see. So, for example, primes tend to be odd. There's only one exception, 2. And that shows up here. So every other column in this picture is just all white. This laser pen can't show you, but only at the very top left corner can you get 2 adjacent primes. Otherwise, you have these big white columns. The primes only occupy every other column here, so they're all odd. There are other patterns like this. They all happen to be adjacent to multiple of 6. Okay, every prime is either one less than multiple of 6 or one bigger than multiple of 6. But that's it. Well, 2 exceptions, 2 and 3. But every other number, 5, 7, 11, so forth, they're all next to a multiple of 6. It's a good exercise to see why. So that, I think, corresponds to the fact that every so often you get these thick white stripes, which this laser pen is not able to point out, unfortunately. Yeah, so numbers which are made of 2, 3, or 4 mod 6 can't be prime, and those are these thick white stripes you see here. And then there's a couple other things. Like if you look at the last digit of a prime, it's always either 1, 3, 7, or 9, with two exceptions, 2 and 5. But other than 2 and 5, every other prime ends in 1, 3, 7, or 9. And that corresponds to some other white lines here. You can see, but the laser pointer can't show. There are these diagonal lines as well. I think those correspond to multiples of 7 or 11. There are certain all these long lines and things which are free of primes, and that's just part of what the primes do. So even while they look random, there are some patterns within them, but not enough to make them sort of really organized. Right? Just enough to sort of make things interesting. So you've got this sort of weird combination of large-scale structure, like the prime number theorem. You've got local structure, like primes being odd and next to multiple of 6 and so forth. And then other than that, they seem to behave randomly. So you have these three different features of the primes. And over the years, what we've learned to do is we've been able to understand these three features well enough to sort of put them together. And we can't answer everything we know, everything we want to about the primes, but we can answer some things. So there are some results we can do just by combining these sort of phenomena, making them more quantitative. So just to give you some examples, so one very famous theorem is Vinogrado's theorem. It's okay. So the statement is that every large odd number n, of course, is not prime necessarily, but you can always write every large number as a sum of 3 primes, even if it's not actually prime itself. So he was trying to solve what's called Goldbach's conjecture. So Goldbach's conjecture, in fact, Christian Goldbach 300 years ago, or 250 years ago, conjectured that every odd number, in fact, bigger than 5, should be the sum of 3 odd primes, 3 primes. So like 11 should be, 7 plus 2 plus 2. Okay. Every odd number should be the sum of 3 primes, and also every even number bigger than 5 should be the sum of 2 primes. So there's two conjectures, the odd Goldbach conjecture and the even Goldbach conjecture. So we don't know how to prove either of these, but in some sense we've almost proved the odd one, because Vinogradov said, well, maybe not every odd number is the sum of 3 primes, but every sufficiently large odd number is the sum of 3 primes. So if you make your number big enough, you're guaranteed to be the sum of 3 odd primes. That's a great theorem, actually. It uses the kitchen sink, actually, but to prove. But of course, there's this sufficiently large business. What does sufficiently large mean? Vinogradov, when he proved this, he didn't say, but later mathematicians went through his proof and tried to work out exactly what sufficiently large meant, and they've been refining this over the years. The most recent result in this direction is by these two Chinese mathematicians, Liu and Wang, who showed that any odd number bigger than 10 to the 1346 is the sum of 3 odd primes. Okay. On the other hand, using a lot of computer search, basically, it's also known that any odd number between 5 and 10 to the 20 is the sum of 3 odd primes. So as far as a mathematician is concerned, this problem is basically solved. There's only a finite number of cases left to check. But unfortunately, in practice, that's not good enough. Yeah, I mean, everyone believes this conjecture is true, but we still have to somehow check it somehow for the last remaining cases, and we can't just do a brute force search. This is just not possible even with the best computers. Goldbach's conjecture, by the way, is perhaps the only mathematical statement I know of actually that has a popular novel, best-selling novel attached to it. This is Uncle Petros and Goldbach's conjecture. It's about this crazy uncle who loves mathematics and spends all his time trying to solve this conjecture. He never does, unfortunately. But okay. So that's one theorem that we know of. Here's another one. So I told you about the twin prime conjecture, that there are infinitely many twin primes. We don't know whether that's true or not. We believe it's true. There are many strong reasons why we believe it to be true, but we can't prove it. But we have partial results. We have near misses, and this is one of our best near misses on the twin prime conjecture. It's called Chen's theorem. So Chen proved not there's infinitely many twin primes, but there's infinitely many twin almost primes. So numbers p where p is prime, and then you add 2 and you get another number which could be prime. If it was prime, you get a twin prime. It's either prime or a product of 2 primes. It's what's called an almost prime. So primes have no factors other than themselves and 1. Almost primes have very few factors. If you have a product of only 2 primes, you only have, I think, 4 factors. So this is close. This is very close to the twin prime conjecture. You have 2 numbers, one of which is prime, one is almost a prime. It's one of the best results we have. The proof is quite complicated. I'm not going to give it here. But actually, the basic idea is very simple. That's one thing about mathematics. Often you have very complicated arguments, but they come from very simple ideas. The basic idea here is to use what's called sieve theory. Sieve theory is a way to create primes by starting the integers and still crossing out all the non-primes before you get to the primes. So in primary school, you should have seen the sieve of Eratosthenes, which is shown over here. If you want to find all the primes up to, say, 64, what you can do is that, well, you don't think of 1 is not prime. You take 2, and you cross out all the multiples of 2. You take 3, cross out multiples of 3, 5, cross out multiples of 5, and 7, cross out multiples of 7. And once you do that, everything else, anything that's left, actually will be automatically prime. Right? Because you've crossed out all the primes less than the square root of 64. That's why it works. So this is a cheap way to generate primes less than 64. You can also generate twin primes by a version of the sieve, but you have to use a much fancier sieve before you can actually prove this theorem. The sieve of Eratosthenes is not good enough at all. You have to use a much fancier one. But okay, but that's how you prove that. Okay, here's my theorem with Ben Green that I proved a few years back. So some patterns like twins, we don't know how to find in the primes. But there are some other patterns that we actually can do. For example, a few years back, I showed with Ben Green that the primes do contain another type of pattern, not twins, but they can contain arithmetic progressions of any length. So an arithmetic progression is a sequence of numbers that are equally spaced. And so, for example, 3, 5, and 7 is a sequence of primes equally spaced. The spacing is 2. That's a progression of length 3. And then the next one here, 5, 11, 17, 23, that's a progression of length 6. Of length 4 and spacing 6, and so on and so forth. Over here, each row is, I've shown the first progression that we know of that length. So this is a progression of prime numbers of length 5, and length 6, length 7, and so forth. What you find quickly is that if you demand longer and longer progressions, you have to go to bigger and bigger numbers. And in fact, even with the best computers, the longest progression that anyone's ever found is of length 25. It's this progression of primes. It's this beast over here. But what we showed is that actually this goes on forever. If you want to find a progression of length 100, which consists of primes, it's out there somewhere. We don't tell you where. It's like Euclid's theorem. Euclid's theorem tells you there's infinitely many primes, doesn't tell you where they are. Unfortunately, a lot of proofs in number theory are like this. They're not particularly effective. They can tell you things exist, but they don't tell you where they are. An analogy is if you have a box and you want to show there's something in the box, okay, you could open the box and look into it, and if you touch something, right, then you know there's something in the box. But a lot of things in mathematics are not like that. We have a box, and we can prove there's something in the box without opening the box. And we do things like we take the box and we weigh it. Okay? And if the weight of the box is larger than the weight of an empty box, that tells you there's something in the box. But it doesn't tell you what it is. And that's actually our proof, to oversimplify quite a bit, actually, works like that. We look at all the arithmetic progressions of primes from all the numbers from 1 to n. That's like a big box. And we count how many of them there are. There's a formula for how many primes there are, progressions of primes there are in this box. And that's like weighing this box. And we show that this weight is quite large. And that tells you that there's lots of progressions of primes. But it doesn't tell you where they are. So anyway, so that's part of the proof. There's no way I'm going to give the whole proof here. It's about 50 pages long. But it does use very much these themes of the primes having both structure and randomness. What we do is that there's actually a way to split up the primes into a bit which is very structured, like very periodic, and then there's a bit that's just completely random. And there's a way to split it up. We don't really understand how this decomposition works, but we know that we can split it up, and we know that both the structured part of the primes, very periodic sequences, and also very random sequences, they both contain lots and lots of progressions. And so no matter how the primes are split up into structured parts and random parts, they're always going to create progressions. And that's how we solve this problem, very roughly speaking. So that's one thing that I did. I'm still working on that kind of thing with several other people. Just to give you one example of the type of thing I do these days. So a few years back, I demonstrated something similar, not for the primes, but for something called the Gaussian primes. So primes are the integers which are not divisible by smaller integers. Gaussian primes are the Gaussian integers, which are not divisible by smaller Gaussian integers. Now, Gaussian integers are complex integers. The numbers, complex numbers, you know, for real part and imaginary part, but they're both integer. So 3 plus 4i is a Gaussian integer. And some Gaussian integers are prime, some are not. In the background here, what you see is a plot of the Gaussian primes, I think of magnitude less than 100. It's a Cartesian plot, but we haven't plotted the axes. Yeah, so there's this nice pattern here. Actually, my friend Ben Green gave me a linen cloth with this pattern for my birthday. It was quite nice. So what we showed, so the Gaussian primes go on forever, just like the ordinary primes. And what I showed is that the Gaussian primes, so we know the primes contain arithmetic progressions of any length. You can also show the Gaussian primes contain constellations of any shape. So what's a constellation? So the way I like to explain this is that there's this movie called A Beautiful Mind, stars Russell Crowe as an Aussie. And he plays a mathematician. And there's a scene there where he's trying to impress his girlfriend, and they're looking at the night sky. And so he asks his girlfriend to name a shape, any shape. And so she names a shape. I think it's an umbrella. And so he looks at the sky, and he thinks a little bit, and she finally points out, like, 7 or 8 stars in the sky, and they make a shape of an umbrella. Okay? And the girlfriend is impressed. Okay, so that's that scene. So okay, so my theorem here, what it shows is that you could play this trick with the Gaussian primes with any shape. Basically, you can pick an umbrella, and somewhere in the Gaussian primes you can find 7 or 8 Gaussian primes which form the shape that you specify, as long as the shape consists of rational coordinates or something. But okay, but basically, so you can find big squares of Gaussian primes if you want. You can find progressions. Yeah, they're all out there somewhere, and it's a variant of this type of thing. So, okay, so this is just a very, very quick tour of prime number theory. There's a lot more going on, of course, but this is just the highlights, or a very few highlights of what's going on. Okay, thank you very much.
This is ABC Fora.